So how does cyclin CDKs catalyze progression through the cell cycle? We've talked about how they are regulated and how they regulate, but how do they achieve the different phases of the cell cycle? That's what's going to happen in this video. And it turns out that the first ones that we're going to encounter, the G1 cyclins, do it by regulating the cell cycle. They lead to the enhanced production of cyclin E, and therefore the progression into S. So it's basically what we've been talking about all along. It just so happens that the inputs are very, very complicated. And this is back to Wikipedia, and I've said many times that I'm going to make this really simple when we get to the cell cycle, so it's time to do that. So we'll just take one of the many inputs that does essentially the same thing, because your book focuses on it. That is MYC as a regulatory transcription factor associated with activated MAP kinase pathways. Basically what you can think of is the only thing that it does is lead to the expression of cyclin D. And that's important because once you get more cyclin D, the concentration of cyclin D CDK4, the G1 phase cyclin CDK, now exceeds the concentration of everything that is trying to inhibit it. So that tips the balance in favor of the production or release, really, of a general transcription factor associated with the S phase, this E2F. And the most important thing associated with its activating genes is that it activates cyclin E expression. So then you have cyclin E CDK activities exceeding the inhibitors that are trying to prevent it from working. And then it's, here we go. Fasten your seatbelt, because we're going through the cell cycle once this happens. And I've mentioned this before, that there's a zillion things going into the nucleus information-wise, and almost nothing coming out. One of them is cyclin E. The other is genes that are associated with apoptosis. One of them is this ARF. This is not actually the same ARF that we talked about with vesicular trafficking. It's alternative reading frame, but it's associated with the ability of DNA repair checkpoints to prevent cycling the cell cycle or to trigger apoptosis. So I'll mention that specifically later on, but while I'm on the topic of things that are named the same, this APC is not the same one as the one that we're going to talk about in the context of mitosis. It's a completely different complex. Very important, but not the same thing as the APC of the Wnt pathway. Okay, so let's get to the business of how. How do we get, once we've activated the gene for cyclin D, how do we get S-phase cyclin activation? And that's shown in these slides, one of which I don't know where I got it from, but I love it, so I keep using it, and the other is from your text. So we'll do this one first. What it shows is the importance or the necessity for having growth factors to get past start, or the restriction point. And that is ultimately leading to overexpression of D-CDK versus the inhibitor of the cyclin D-CDK complex. Once that happens, then you get phosphorylation of a particular protein that was not phosphorylated before that. So basically, passage through start is the addition of these phosphate groups on this protein RB, retinoblastoma protein. The significance of that is that it is an inhibitor in the unphosphorylated form of a transcription factor that is associated with many genes of the S phase, the most important one for us being the gene for cyclin E. So you take this thing through. Growth factors activate cyclin D CDK4, which phosphorylates retinoblastoma protein, which leads to the release and therefore activation of a transcription factor that turns on genes that are required for DNA synthesis, including cyclin E, which then associates with its CDK and phosphorylates more RB protein, leading to the release of more E2F, leading to more activation of genes associated with the S phase. So you get this very nice feedback activation built into the passage through start and into the rest of the cell cycle. So your book has a longer description beginning with growth factor, mitogen, the same thing in this case, leading to MAP kinase, leading to the production of active MYC, which then turns on the genes for active cyclin CDK. So here we have the inactive form of E2F associated with active retinoblastoma protein, no phosphates on it. Once you have an excess of CDK, cyclin D site CDK over the inhibitors, then you get phosphorylation of RB. It dissociates from E2F, and then E2F does that positive feedback activation and ultimately triggers the steps that are part of the S phase. So why is this RB unphosphorylated at this stage before we get to start? So this is in really it starts in late M phase and proceeds as long in G1 as the cell is not going through the cell cycle. And this could be for the life of the cell, basically, because some cells divide 25 times and then never divide again. So that would be the state that they're in, no phosphate groups. And this is related to that concept that I mentioned back in the introduction, this period right here where phosphatase wins. So this is why this becomes this in going from this period where there is kinase activity associated with some cyclin CDK to a point where there is no kinase activity, and therefore those phosphate groups are removed. So among those that are removed are the ones that are on RB, which then associates with E2F and then essentially promotes the maintenance of G1 for as long as it takes, as long as the cell is not being exposed to a mitogen. So when the next mitogen comes along, if it ever does, then the whole process starts all over again. So it's a very, very simple mechanism. Really, it's just turning on genes for cyclin D, and the rest takes care of itself. It's just that that process is very tightly controlled by things that monitor the activity of the cyclin D CDK and that control the activity of this very, very important regulatory transcription factor.